Okay. So we talked about the difference between water-soluble and lipid-soluble hormones. Understand the difference between the two. Mechanism of action. What's the difference between the water-soluble and lipid-soluble? Say it again. Think hormone mechanism of action. How it works on the cell. So a hormone can only work on cells that have what for that hormone? Receptors, right? That's the hormone's what? Begins with a T. Target. Now, if I'm a water-soluble hormone, I come in contact with the receptor and something happens. What? You're all in a coma. Obviously, we didn't read over our hormone chapter on Tuesday. I'm going to come in contact with the receptor and set off a second messenger system, right? We talked about one, the cyclic AMP second messenger system, right? Yes? Somebody go yes, so Maria knows she's in the right class. Good. Remember that whole spiel I gave you? Yeah, the little G protein and adenylate cyclase and causes changes within the cell, make different proteins, do a different thing. Yes? Good, I'm glad you're awake now. So that's water-soluble hormone. Lipid-soluble hormone is going to do what? It's going to what? No. Somebody said DNA would change the what?
The mRNA messenger.
Yeah, which will result in what? A different protein being produced. So the lipid-soluble hormone is actually going to come in contact with its receptor on the target and do what? I thought I'd throw the picture up there to help you out a little bit. It's going to do what? I'm giving you a hint. Yes, it's going to go into the cell. Whew, you're making me work hard today. So it's going to enter the cell, then enter the what? The nucleus. And it's going to come in contact with a binding site for that hormone on the genetic material itself. That's going to change what transcription and translation is going to do for me, change the protein that is produced. And new proteins will cause new actions within the cells. Yes? So water-soluble comes in contact with the receptor, but never does what? Doesn't go inside the cell. It causes a chain reaction within the cell. Lipid-soluble hormones do what? They come into the cell and they cause change at the DNA level. Yes? Phew! Different ways to cause hormone release. Know those. Humoral. What's a humor? Some sort of fluid that runs through the body. So blood, for example, they give us an example of low blood calcium triggering the release of what? It's going to trigger the release of a hormone. That hormone is then going to cause the change. You see where we're going? So what's quicker? The nervous system zapping something, causing changes, or releasing hormones that come in contact with cells that cause changes within the cells? The nervous system's faster, but there's so many things to regulate throughout the body. The endocrine system is going to do that what? It's going to keep it going, keep that balance going on a regular basis, more even, more uniform for longer periods of time. Does that make sense? So 3 different ways a hormone can be released. Some kind of change within the blood. The nervous system can zap it and it can release. And other hormones can cause the release of a hormone. Yes? Say yes. Good. See, I shut the lights off. They're all in a coma. So, nervous system interaction of hormone at the target. So, there's 3 different terms they give us here in the textbook on page 598. They talk about permissiveness, synergism, and antagonist. So, we can work together, synergistic. We can cause something to release, permissiveness, or we can stop something from being released, and that's an antagonistic relationship. So hormones in the endocrine system can do several different things. They can stimulate things to happen, they can work with other things to cause change, or they can stop things from happening. So all of those things are part of what the endocrine system is about. Now the next thing the book goes to do is break down all of the different endocrine organs and tells us what? Tells us where it is, what it makes, and what its target is. So what are the results? What change is it going to cause? Remember, that's what you are going to make that chart for. There's tables in here too that you can cheat from. Did you notice that? Okay, good. So the first one's the pituitary gland. Where am I going to find the pituitary gland? It's in that midbrain region. It hangs off a little stalk called the infundibulum. Right below the hypothalamus. Now we're going to find out, I think we talked a little bit about it last semester when we talked about the nervous system, but the hypothalamus is an extremely important part of that central brain region. Not only for all the other things we talked about last semester, but for neuronal control and hormonal control in this chapter as well. So we have nuclei in the hypothalamus that actually make hormones. And those hormones are stored in a portion of the pituitary gland. So when we look at the pituitary gland itself, it's actually 2 different lobes. We have one called the anterior pituitary gland, and we have one called the posterior pituitary gland. Now the posterior pituitary gland doesn't make hormones. Do you know what it does? It holds on to them. It stores them. Stores them. Who makes them? Who's right above? Nope. The hypothalamus. So those neurons in the hypothalamus produce hormones, oxytocin, an antidiuretic hormone, and they're stored here in the posterior lobe of the pituitary gland. There's another name for the pituitary gland. Sometimes they call it the master endocrine gland. I think it's got named improperly. You know who I think the master is? Hypothalamus. Hypophysis. Adenohypophysis, neurohypophysis. Another name for anterior pituitary, posterior pituitary. Okay? So the posterior pituitary gland basically stores up, and when it's necessary will release hormones that were made in the hypothalamus. The hypothalamus is going to help let that release know when it needs to happen. What's antidiuretic hormone? Yep, holds on to more water. So what do you think antidiuretic hormone is going to help me do? regulate fluid balance. It's going to affect cells in the kidneys. So when it's time for me to hold on to a little water, maybe I am a little dehydrated, antidiuretic hormone is going to be released, and it's going to affect the kidneys by causing the cells that normally would get rid of water to do what? Hold on to water. Yes? What's oxytocin for? Yeah, childbirth. So, that's a posterior pituitary gland. The anterior pituitary gland, on the other hand, looks very different. Tons and tons of different cells that are going to make many different hormones. What are some of the hormones the anterior pituitary gland makes? Growth hormone, TSH, thyroid stimulating hormone, ACTH, adrenocorticotropic hormone, FSH, follicle stimulating, LH, luteinizing, PRL, prolactin. All of these guys are going to go stimulate somebody else to do something in the endocrine system. That's why we call the pituitary gland the master, because it is going to help regulate other endocrine glands within the system. So this is an example of what type. Remember that little chart I just went over? These hormones are an example of what kind of stimulus. On page 597, hormonal stimulus. Because TSH is going to stimulate the thyroid to do its thing. FSH is going to stimulate the gonads to do their thing. Yes? You with me? So, the book goes on, describes the hormones, tells us who makes them, how they're released. Good old chart on page 602 and 603 describes the hormones, describes their target, what their effects are. Okay? Why would I release them when I need X, Y, and Z? So we need to know those. So maybe that's an extra thing you can add to your list. Again, when you make this list, don't copy all of the words from the table. You know what I'm saying? You want to make it small. So, all of those guys, you should know what they do for us. Understand one thing about the endocrine system. Hormones might not necessarily just affect one thing. They can have side effects. So they have a certain thing they have to do, but they can also, to achieve that thing, affect other systems. So growth hormone, for example, this is an example of how the endocrine system works. They block it out for us. Growth hormone has a very direct action. When we think of growth hormone, we look at the chart, fat metabolism, carbohydrate metabolism. That's going to end up increasing blood glucose, increasing fat breakdown. But an indirect action of the same hormone is also going to have an effect on the liver and other tissues. Skeletal, extraskeletal muscle. It's going to cause increased cartilage formation, skeletal growth, increased protein synthesis, so that I can do what? So that you can grow. So growth hormone has a very direct action, but also has an indirect action throughout the body. Insulin's the same way. Insulin is going to be released by the pancreas and help you get glucose into your cells. That's the thing everybody knows it for. But it's also going to cause you to store any excess glucose that you have as well. So it also, as a side indirect action is also going to increase fat metabolism and fat storage. Did you know that? So all these hormones kind of have a direct and indirect action throughout the body. So understand the hormone, what it does for a living. This is an example of a problem with which hormone? Growth hormone specifically. Too much, too little. And some of you might have experience with this already. Know somebody that is slow growing, or some children that are slow growing. One of the first things that comes to a doctor's mind is to check what? Hormone levels, to make sure that these hormones are being produced at the right rate so that growth and metabolism is happening at the right rate. So, hormones can have a big effect on growth in this case. Thyroid stimulating, all of those are gonadotropic releasing, follicle stimulating, prolactin. That's going to help with what? Milk production. Excuse me. And that's the pituitaries, anterior, posterior. When you look at them under the microscope next week, make sure you pay attention to the different structure. The anterior pituitary gland, you're going to see nice big fat cells, because those cells are the cells that are making what? I got a drink, I can wait. Anterior pituitary gland. It's making hormones, right? When you look at the posterior pituitary gland under the microscope, you're not going to see a lot of big, huge, fat cells. You're going to see a lot of, like, axons almost. There's some areas where the hormone is stored, but mostly you're going to see, axons. Very similar to what you saw when you looked in the nervous system. So physically you see the difference under the microscope. So that hopefully will cement the difference between the function of the two. Yes? See, that's why we do lecture and lab. Yeah. Okay, who's this? This is our next guy, our next victim. Thyroid. Looks a little different because what we have is the cells that make the hormones that kind of hang around this big empty space. What's the big empty space? It's filled with colloid. I call it the thyroid hormone soup. Because the cells, the follicular cells that actually produce the hormones, it takes a while to do. It's a little bit of a slow process. So the nice design with the thyroid is the cells can constantly sort of make stock and store that stock in the colloid. Super Bowl's coming up, right? Where do we find the thyroid, by the way? In the neck region. When we talk about the respiratory system, we're going to talk about the larynx and the cartilage that covers the larynx. You know what it's called? The cartilage is called? It's called thyroid cartilage. Why do you think it's called thyroid cartilage? Because that's where the thyroid sits. Okay? So, right around that larynx region, we find the thyroid. And when you look at it under the microscope, very distinct. You have cells around this nice big pink soup. Now, on page 608, figure 16.10. This would make another wonderful essay question on your next exam. The steps of producing thyroid hormone. Now, I love it that you guys are taking AMP2 now because it's perfect. It's a perfect visual for me to set out there for you. Super Bowl Sunday. Does anybody have a party? What do you got? Yeah, it's this Sunday. Even though, it's uneventful, I'm in it for the food and the commercials, okay? For football, I don't know. But you guys have parties? You know what we do for Super Bowl? We do it every year. We have the big sandwich. Yes? And then I make a cake that looks like a football. It's quite good. I've perfected it over the years. It looks exactly like a football, and it's quite tasty. But big sandwich. Keep that in mind, because this is sort of how the colloid is made. In order to make the thyroid hormones, and they have big, huge, long names. Triiodothyronine and thyroxine, T3, T4. I'm good. Yes? Those are the thyroid hormones. And we have to make them in a couple. We have to get ingredients to make the hormones or the Super Bowl sandwich from a couple different places. One of the very important ingredients to making thyroid hormone is iodide. And iodide has to be transformed into iodine. Iodide has to be transferred into iodine in order to use it in hormone production. So it's going to be absorbed in through the circulatory system. What are these yellow things? Excuse me. Pardon me, you're going to get lots of coughing in your video. These are the cells. These are follicular cells. And what's this? That's the colloid. Okay? So we have to, through the circulatory system, absorb iodide. We've got to kind of transform it to iodine and shove it into the soup. The other part of the molecule that's very important to produce is going to be produced it's protein in nature. So the rough endoplasmic reticulum and the Golgi apparatus are going to help me make that part. If you look at the diagram, they're called tyrosines, the little purple things that look like bacteria. Yes? Those are going to get produced in the endoplasmic reticulum. They're going to get packaged and shipped to the colloid by the Golgi apparatus. We call the thyroglobulin synthesis in that region of the cell. Now the book goes on and on a little bit about all the chemistry, but what I want you to remember is the Super Bowl sandwich. Now you're not going to eat the whole Super Bowl sandwich, are you? What are you going to do? You're going to cut a piece off and give it to whoever, and they're going to eat their Super Bowl sandwich, right? When I produce the thyroid hormones, I'm going to make a molecule that's a lot bigger than I'm actually going to use it as. So I make large T7s and T8s in the colloid. And they're combinations of those tyrosine molecules and iodine. I'm going to store those away until I need them. When I need them, who's going to tell me to release them? Not the hypothalamus. The pituitary gland is going to release what? It's thyroid stimulating hormone. That's going to come in contact with these cells. Change. What's the change? Time to cut the sandwich out and send it out to the masses. Time to grab onto those larger molecules from the colloid, use my enzyme knife. Yes? So I'm going to fuse the larger molecules with a lysosome. The lysosome is going to cut it into the pieces in which we need to use it as T3, T4. And then what's going to happen? Use the fancy science term. Exocytosis, exactly. So I'm going to take that vacuole through exocytosis and throw it out into blood as T3, T4. So just like the Super Bowl sandwich, I'm going to cut it up. And who's going to cut it up? The lysosomes, the enzymes are going to act like little cutting knives. And they're going to dole out T3 and T4. Pretty good analogy, huh? Oh. then yeah, it's not going to work for me with the hot wings. You don't want to share your wings. So think Super Bowl sandwich. So that's how thyroid hormone is produced and then actually used. Okay? Use this diagram to help get everything straight, understand the players involved in making thyroid hormone and then using thyroid hormone. Okay? So what's thyroid hormone going to do for me? It's actually going to regulate the rate of what? Metabolism. So it's going to speed up metabolic reactions in different circumstances. Hypothyroid slows everything down. So it slows down the rate of reactions of metabolism in your body. Correct. Because they're not using as much energy as they should, their rates of reactions are going too slow. Now, hyperthyroidism, the other direction, everything's moving too fast. So they're using up too much energy at a faster rate. No, depends. It depends. Well, it depends on why the issue is there. It could be a pituitary issue that's causing thyroid issues. It could be thyroid not making hormone properly. So it depends on the issue. So we see on page 609 a couple of different thyroid disorders. We can get an enlarged thyroid or goiter. And what's goiter caused by? Yeah, iodine deficiencies. Where do you get iodine in your food? It's not naturally in salt. Did you know that? Yeah, you usually get it from seafood, but we recognized many, many years ago in our country that people weren't getting enough iodine because many of us didn't eat enough seafood. So then we started putting it where? We started putting it in our salt. So it's an additive to salt. You can actually buy it without iodine. Did you know that?
What happens to people that are
Right. Well, you get it in other things, but that's one of the easiest ways to get enough in us. We don't need tons and tons of it.
Here's a question.
Yeah.
When I had met Term at KVCC, the nurse who was teaching it had said that her father, and she had noticed that a lot of elderly people, they started acting a little loopy.
Mm.
They are just off. They up their salt intake, and it would seem to even them out. Would
Huh.
that be the iodine?
Might be. Or it could be sodium, potassium, electrolyte imbalances too. So, and a lot of problems with some elderly people is, diuretic issues, fluid issues. They might be losing too much electrolytes. So there's so many other factors to something like that, but that could be why. Okay? So, the synthesis is described on page 608, 609. The steps are there. You know how I like the steps. I enjoy the steps. So, T3, T4, TSH from the pituitary. Those are guys we're going to talk about when we talk thyroid. Parathyroid. Oh, another one the thyroid makes, I can't get too far ahead, is something called calcitonin. Calcitonin is doing what for me? Now, this is kind of a weird one. It's going to help me store calcium kind of indirectly because it actually inhibits the next guy I'm going to talk about. The next guy I'm going to talk about is parathyroid hormone. And we already got introduced to that guy a little bit earlier. Parathyroid hormone helped what? We talked about this last class. I told you about Mr. Monocyte, right? So when calcium levels drop, what do I have to do? I have to get calcium levels back up. parathyroid hormone secreted by the parathyroid glands, thank you for naming it the same thing, is going to stimulate monocytes to transform into osteoclasts. Osteoclasts are going to go break down bone matrix, release calcium. Calcium levels are going to go up. So calcitonin actually says, hey, enough. You slow down. Does the opposite. So if I go to Friendly's, for example, I always love to use this example because I dream of the peanut, you know those big, huge things with the peanut butter and the chocolate in them at Friendly's Sunday? Lots of calcium from the ice cream. So if I go and have one of those, I have plenty of calcium floating around, right? Do I have to go break down bone matrix? No. What do I want to do with the extra calcium? I want to store it. So by slowing down the breakdown, I allow the osteoblasts to suck up that extra calcium and do what with it? Store it, make bone matrix. Okay? So these guys kind of work in conjunction with each other. Calcitonin is going to allow me to store calcium. Parathyroid hormone is going to break it down. When we look at the parathyroid, again, very different structure. So we see very tightly packed groups of cells that are going to produce the hormones for us. And they're dotted throughout the thyroid gland. So when you go and look under the microscope, you might see two different types of tissue in that one slide, right? The thyroid looks very, very different than the parathyroid under the microscope, doesn't it? Parathyroid, tight packed cells. Thyroid has what? Now you see that big soup with the cells that kind of surround it. Yes? Another feedback mechanism we see on page 611, effects of parathyroid hormone on the bone, kidneys, and intestine. So again, there's a sideshow going on, right? We think parathyroid hormone, osteoclast, break down the bone, yay, but it also has an effect on the kidneys. What's it going to cause the kidneys to do? If I need to increase calcium levels, do I want to get rid of calcium in my urine? No. I want to hold on to as much as I can, right? So it's also going to have an effect, side effect on the kidneys and cause it to increase calcium reabsorption. So I hold on to more calcium. I don't lose it. Because remember, my goal here with this feedback mechanism is to do what? Increase calcium levels in blood. It's also going to increase the activation of vitamin D. What the heck does that have to do with anything? What's vitamin D do for a living? Anybody know? It's going to help me absorb and utilize what? Calcium. So if you just take calcium with no vitamin D, is that going to be an efficient? No. What are you going to do if you don't have enough vitamin D to absorb calcium and utilize it? What are you going to do with? Yeah, you're going to get rid of it. Okay? So those are the side jobs that happens with this particular hormone. Am I losing anybody? It's pretty straightforward, isn't it? So that's the parathyroid, the thyroid. Understand those hormones, what they do for a living. The next one sits on top of the kidneys. And what are these guys called? The adrenal glands. Now there's two parts of the adrenal glands, two groups of cells. There's a group of cells that hang out in the middle of the gland, and there's a group of cells that, what? Of course there is. And there's a group of cells that hang out on the outside of the gland. Now, you've heard these terms before, right? When we studied who? The brain. You had the medulla oblongata in the middle, my favorite word in science. And then the cerebral what? Cortex. So you're going to see the same sort of setup here with this gland as well. So the adrenal medulla and the adrenal cortex. So these groups of cells in both these areas are broken up into different zona. So we'll see they're covered with a nice capsule, and then we see a zona glomerulosa, fasciculata, reticularis, and then we see the adrenal medulla. So you're going to see layers of cells that have different functions. So for the adrenal cortex, we see the hormones here that are going to be produced by that region. And again, the cortex is kind of the what? The outer region. Group of hormones called mineralocorticoids. We're going to talk about, especially when we talk about the renal system, we're going to talk about hormones renin and angiotensin and aldosterone. These are going to help regulate kidney function and water reabsorption. One called ACTH, adrenocorticotropic hormone, is going to be released by who in order to stimulate the release of these? The pituitary gland. So that's going to play a role in the release of these hormones. And another one, ANP, is also going to play a role in this as well. Who makes ANP? Atrial natriuretic peptide, a heart. And that is related to pressure. When blood pressure rises in the system, one of the quickest ways to decrease it is to get rid of excess water. Yes? And remember the renin, angiotensin, all that thing, that was the job of the adrenals, right? So if blood pressure goes up, one of the fastest ways, I can monitor it up in the heart region quick, because that's the pump and all the blood's going through there. I can release hormones, ANP, that are then going to cause the release of hormones from the adrenals. So that's another intermingle of two endocrine glands working together to regulate function. Glucocorticoids are also released by these areas as well. Cortisol, cortisone, corticosterone, they're all going to have or play a role in metabolism, actions of glucose. That's why they're called glucocorticoids. Excuse me. Another group of hormones is called corticosteroids. And these are going to have an effect on who? What's a gonad? Anybody know what a gonad is? Your testes is one. Ovaries are another. What do they do for a living? They make reproductive cells. So these hormones also play a role in the production of those reproductive cells. We're going to see that not only does the adrenals play a role in that, but who else? We met at the beginning of the chapter. Pituitary gland, right? Anterior pituitary gland. You guys are so comatose today.
Together like the ANS and the PNS does, kind of. It starts in and the second half finishes.
Correct, correct. And again, example of how hormones work together. Endocrine glands work together for the same function. The side jobs, like I was saying before. The adrenal medulla. That's in the what? No, it's in the adrenals. It's in the middle. Look at page 616, table 16.3. We see a description of all of the hormones. Okay, so the adrenal medullary hormones, those cells in the middle of the adrenal gland, produce things called epinephrine and norepinephrine, the catecholamines. Okay, and they can have an effect on different reaction rates, speed things up, slow things down. You mentioned sympathetic and parasympathetic before. They act like actions of the sympathetic and parasympathetic division of the autonomic nervous system. But remember, hormones are going to be more what kind of action? Slow and steady. They're going to last longer than something the nervous system could do. Okay? I feel as if I'm losing you.
I think this is going to be hard to study for.
Yeah, and that's why if you make yourself that chart and just kind of at least get the big picture, and then go back and understand some of the side players also involved, at some point you're going to go, ping, ah, I get it. The light's going to go on. But it's one of those things where you have to map it out and stare at it for a while.
Yeah, how to put it together.
Yeah, and use the tables to make that map, but then use the diagrams to visualize what's going on. Okay? Again, what do we have here? This is one of the hormones, aldosterone. And when we talk kidneys, we'll talk more about renin and angiotensin and the renin-angiotensin pathway and what it does and all of that good stuff. But basically what we're going to do here is change what's going on in the kidneys. We'll talk about this when we talk fluid and electrolytes. We'll talk about this when we talk about the renal system. But if I want to hold on to more water, I can't just tell the kidneys and the cells to absorb more water. I actually have to absorb something that water's going to follow. Now back to your chemistry chapter. Oh, I know, you didn't think you had to know that crap. Yes, you do. But water is a polar covalent molecule. Remember that? What's that mean? Yeah, it's got a slightly positive end and a slightly negative end. So it's got a slightly negative end and these are the H's, and that's the O, a slightly positive end. Yes? Even though it's a neutral molecule, it's got a little bit of a polarness to it. So if I increase the absorption of sodium, I'm also going to increase the absorption of what? Water. Yes? In this case, because of our sodium-potassium pump, we're going to do the opposite with sodium and potassium. So if I increase potassium excretion, I'm going to increase sodium absorption. If I increase potassium absorption, I'm going to increase sodium what? Excretion. So the quickest way to regulate volume with the help of these hormones is to target the kidneys. Because the kidneys are constantly filtering your blood volume. That's what they do for a living. Get rid of excess water, get rid of excess waste products, get rid of excess ions, get rid of excess hydrogen ions to regulate pH. That's what the kidneys do for a living. So a quick way to affect pressure in the system is to call on the kidneys and affect water balance. So we see the guys mentioned from the adrenals, renin, angiotensin, the ACTH from who? Who made ACTH? Pituitary gland. The ANP from who? The heart. They're all going to work together to do what? Increase blood volume, and therefore very quickly increase what? Blood pressure. Those guys can also work together to do the opposite. Yes? So when pressure goes up in the system, they can do what? Cause it to go down fairly quickly as well. This is a diagram we see on page 615, the effects of too much what? What's Cushing's syndrome? It's a problem with who? With ACTH. Cushing syndromes and things like cortisol. Some of these guys, the glucocorticoid drugs, for example, are something that are going to help with this particular syndrome. Addison's disease is also described here as well.
So, like, my friend had a kidney transplant, and she was like teeny tiny, whatever. And then she went on like all the meds after that, drugs and all that. And now she's like glued right up. And she
Yeah, but it might not necessarily be fat with her. It might be fluid.
So that's what I was just looking, because like some of this kind of looks like her, so I'm like, is that?
Yep. And it's fluid problems with fluid regulation. Yeah, and you get puffy in the face, puffy in the extremities, and that has a lot to do with fluid regulation. If I want to regulate fluid quick, again, I'm going to target the kidneys because they can do that fast. So usually treatments for people who are holding on to too much fluid target the kidneys and cause what to happen? The kidneys to release more fluid. So if I want to release more fluid, I take a what? Diuretic. What is ADH? Antidiuretic hormone. It actually does the opposite. See?
Good question. When a friend had the kidney transplant, would the brain and all the hormones that were still her own still be functioning on the fact that the kidneys were non-working, and it takes a while for that system to mesh up?
Hopefully she has at least one working adrenal gland. Yes. That's
He was in the NICU for 9 days because his pancreas would not work. He just, his pancreas. But anyway,
Yeah.
because I was producing so much sugar, he didn't need to produce any.
yeah.
So I didn't know if maybe that it takes a while for those two systems to.
Yeah, and it depends if the patient doesn't have proper levels of the hormones from the adrenals, they're going to have to take drugs to help supplement the actions of those. Yeah. 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 And again, because of the chemical imbalances, you know, we take for granted what a fine mix chemical balance there is in our bodies. So this diagram, and some of you might be feeling this as well, show the effects of prolonged stress on some hormone release. Because can stress affect hormone release? Yes, it can. So short-term stress can do things like increase heart rate, blood pressure, mess with your bronchioles, breathing. Do you ever get really scared and feel like you're going to pass out because you can't breathe? Yeah. Liver is going to convert glycogen to glucose because you're all kind of crazy and spastic, and what are you doing at a faster rate? Burning up glucose, so you need more energy. Blood flow is going to change, metabolic rate's going to increase. Long-term stressors can cause problems like this. Mess with your kidneys, because your kidneys are going to help regulate all of these wonderful things. Blood volume and blood pressure can be a problem. So high blood pressure is a result of long-term stressors. Proteins and fats converted to glucose are broken down for energy. Glucose increases. So type 2 diabetes can also be the result of long-term stress. Stress is not good. One of the things you should, and your immune system gets suppressed too. So you get sick all the time. So who in this class thinks they might have long-term stress effects? So what do you need to do? You need to chill. Exactly. You have to, especially when your life gets crazy and stressed out, you have to remember to take a step back, even if it's for 20 minutes a day, and breathe. My best advice to you. So do that. Do any of you do that? Yeah. You do? What do you think after you're done? You and I told you to, right? Yeah. And what do you think, though? Is it helping?
Oh yeah, huge.
Because it allows you to put things in perspective. It allows you to just disconnect for a few minutes. It doesn't have to be for hours and hours. 20 minutes. You can do that.
But then when you get back to even if I'm studying and I'm I'm getting this 5 minutes.
Yeah, then walk away.
I walk away and I come back because I'll sometimes I'll go for half an hour and then I'll come back and I feel so recharged and I feel
Yep.
oh yeah,
Yeah, because look at what's going on, not only neurologically, but chemically with all of these hormones. They're going nuts. We want to get them back into check. We want to even out. And when you do that, when you disconnect, when you give yourself that 20 minutes to relax, to disconnect, you can really get things back into balance for yourself. So do that. Do yourself a favor. You deserve it. That's right. Okay, who do we talk about next? That's the adrenals, adrenal cortex, adrenal medulla. Again, use that wonderful table on page 616. Understand what stress does to some of the different hormones. What's a pineal gland? Anybody know? It makes something called melatonin. And I think many of you have high levels of melatonin in this class today. It makes you sleepy. You actually do, believe it or not, have higher levels of melatonin this time of year. Do you know why? Less sun exposure. So no matter what, us Mainers, we're all kind of in the winter because we don't get as much sun exposure. It regulates your sleep and awake cycles. As we get older, the decreased production of melatonin might cause problems with those sleep and awake cycles. We talked about them last semester. Remember all the nice rapid eye movement and stage 1, 2, 3 sleep, yes? So as we get older, sometimes we don't sleep so good anymore. So there are supplements you can take, and one of them is melatonin.
Are you still doing the cherry juice and the cherries?
I keep forgetting. I have the cherry juice, but I keep forgetting to drink it. It actually works pretty good. Tart cherry juice. I read that in Prevention magazine. Because I don't like to take drugs. I'd rather not. If I can do something dietarily that it's not going to have an effect. If it doesn't work, it doesn't. Big deal. So I drink cherry juice. It's not going to kill me, right? But I'm not too crazy about taking medications. So I like to try these little things. But the cherry juice actually does work. So when I remember to drink it. Sometimes I get into bed, it's like, I didn't drink my cherry juice. And then I'm too lazy to get up and go drink it. Okay, pineal gland. So melatonin, remember that. That's kind of our regulator of our biological clock. Other endocrine glands and tissues, the pancreas. The reason we put it under other is because the pancreas is not only an endocrine gland, but it's an exocrine gland. So we're going to revisit this guy when we come back to the digestive system, and we'll talk about its functions there. But what we see in the pancreas is groups of cells, and again, when you look under the microscope, you're going to see these little balls with groups of cells that have two different types of cells. There's alpha cells and there's beta cells. And they hang out in these areas called the pancreatic islets, or the islets of Langerhans. So some German guy probably figured this one out, right? So Glucagon and insulin produced by these two separate cell types. Beta cells produce insulin, alpha cells produce glucagon, and together they work hand in hand to help regulate what? Yeah, your blood sugar, glucose levels. So we've talked about these guys before, right? Every time I yell at you because you don't eat breakfast, we talk about these guys. But when blood glucose levels start to go up, pancreas is going to make insulin. Insulin is going to help your cells suck that glucose in so it can use it to make energy. When blood glucose levels start to go down, I'm going to want to break down some of my stored glucose. I store it in the form of glycogen. I store it in places like muscle tissue. I store it in places like the liver. So the pancreas and the who cells, alpha cells, are going to produce who? Glucagon. Glucagon is then going to cause cells to break down glycogen. Glycogen is the stored form of glucose. Yes? You guys are so, you wicked comatose over there in the corner. Totally in a coma today. We're going to have to bring margaritas to class or something and get you guys going. All right, so glycogen is going to be broken down in the presence of glucagon. Insulin is going to help me bring in. So here's a question. Insulin's going to help me bring in glucose to the cell so I can use it. Now, not only to make energy, but what else do you think insulin's going to help me do? And I said this before, so coma people, I said it already.
What was that question? Yeah. I'm not even following the question.
Besides insulin causing glucose to come into the cells so I can use it faster, what else do you think it's going to cause the cells to do with glucose? Store it in the form of what? No, ATP is when I use it, right? So I'm going to do some of it, I'm going to make ATP, but then if I want to store glucose, what am I going to make? Fat or? Can't make muscle cells. You already got them. What did I break down to get the glucose? Glycogen. So insulin's also going to stimulate what? The production of what? I just said it. Glycogen. Wow. Wow. Oh my gosh. Yes? We good? So, pancreas, glucagon, insulin. Understand what goes on with those guys. Just learn it all. When I have problems with insulin, we're all very familiar with this disease, I think. Diabetes. Now, there's different kinds of diabetes. I can have problems with my pancreas making insulin properly. I can have problems with my pancreas making insulin at all. Or I can have problems with the receptors on the cells for insulin. Now, which cells do you think carry receptors for insulin in our bodies? No, receptors for insulin. Which cells? This is kind of a trick question. Let's put it this way. If the cell doesn't have a receptor for insulin, is it going to be able to get enough glucose to make enough energy? So now that I've said that, which cells in our body have receptors for insulin? All of them. Very good. Yes. This side of the room wins. You guys are still in a coma. Right? So there might be, as we age, as we get older, a problem with our cells making those receptors. This is kind of a lock and a key thing, the hormone and receptor. If the receptor is not the right shape, the hormone can't react with it, right? So those are the different types of diabetes I can have. Type 1, type 2 describe different effects related to insulin or the working of insulin, the ability of the cell to get what it needs to make its energy. The other thing they talk about in here are gonads and the placenta. Those make hormones for us as well. When we talk about the reproductive system and we talk about pregnancy and development, we'll talk about some of these hormones. Estrogen, progesterone, testosterone, all involved in some way producing those reproductive cells or helping to maintain the placenta for pregnancy. So in some way, shape, or form, in different ways, helping with the reproductive process in humans, both males and females.
Do you want us to know this?
Yep. You won't just know everything. Hormone secretion by other organs. Adipose tissue makes hormones. Leptins. What do leptins do for me? Yeah, appetite suppression. A lot of drug companies who are trying to invent the magic drug that's going to make us all gorgeous and beautiful have studied leptins for years. Gastrointestinal tract, when we talk about the digestive process, there's a whole bunch or a whole group of different hormones different cells will produce at different times. And you'll hear me say this when we hit the digestive system, to signal the tube as to what's coming. So different process in the digestive process. We eat food, right? We chew food. That mechanism of chewing and making saliva and swallowing is going to signal cells in our stomach that something's coming. Cells in our stomach are going to make different things to prepare that food and also to signal the intestines that something is coming. So the intestines can be ready to do their thing. So in this chart, we see a whole bunch of hormones that are secreted by stomach. That's kind of the beginning. Duodenum is the beginning of the small intestine. And these hormones are going to help prepare the next part of digestion by signaling the cells in the tube next to come. You don't have to memorize all these guys. Just be familiar with the fact that they are gastrointestinal hormones that are going to help with the digestive process. So cholecystokinin, secretin, ghrelin, these are all hormones that are going to help with digestion. Adipose tissue, leptins, resistin, excuse me, just general where they come from and help with fat metabolism. Heart, ANP, atrial natriuretic peptide, that's going to help with, indirectly with, regulating who? We talked about this. Blood pressure, thank you. Kidneys, when we talk blood, we're going to hear this guy's name again, erythropoietin. What do you think erythropoietin does for a living? It's going to stimulate the production of red blood cells. The skeletal system also gives off some hormones that are going to help increase insulin production. The skin is also going to help with some hormones that are going to help activate vitamin D. So we call vitamin D sometimes the sunshine vitamin because the rays of the sun are going to help increase this process. And the thymus we're going to talk about when we talk about the immune system. And I fondly refer to the thymus as T-cell kindergarten. Now, T-cell kindergarten is the place where your T-cells are going to go to learn about your cells. Your T-cells are responsible for protecting you from foreign invaders. So what your T-cells have to learn is what your cells look like. And where are they going to learn that? In T-cell kindergarten, the thymus. So hormones like thymulin and thymopoietin are going to help with the activation and maturation of those T cells. So basically in this chapter, you're going to kind of get a taste for what everybody does. And then as we go along and discuss all the rest of the systems, we'll talk about them in more detail. Okay? So don't spaz about knowing every single thing, because we're gonna study them again in much more detail.
Next exam, is it over 15, 16, and 17?
Correct.
So it may not be next.
Get out your clickers! Now, did everybody sign the sign-in sheet? Yes? Did you put your clicker number on there? All right. Which group of messengers is defined as acting on cells within the same tissue? Kind of a cruel question, but I threw it up there anyway.
Are we voting?
We're voting. Everybody vote? Well, hurry up! 5, 4, 3, 2, 1. What's the answer? C is the answer. Very good. Okay, how do we do this again? Oh, we had to go down here, right? Chart type. Correct answer. C. All right. So para means what? Beside, together. Yes? All right. A major difference between neurotransmitters and hormones is that hormones are secreted Five, 4, 3, 2. What's the answer? D. This is a pain. Oh well. Oh boy. Okay. Not bad. All right, and let's throw out one more. A major determinant of a hormone's mechanism of action is what? That's not a choice. Jesus cannot help you now. We got some work to do, I'm guessing.
I wasn't stressed.
You weren't stressed? Now your adrenals are going crazy. 5, 4, 3, 2. for? What's the answer? The answer is A. Whether they're lipid soluble or... That's how we started our discussion this morning, oh comatose friends. You got it right? Oh, good. Good. Okay. So, you got some studying to do, I think. I'm going to put up your quiz when I get back to my office. It will be due before class on Tuesday.
You still dropping the lowest score?
Yes.
Thank God.
I don't know. I might have to drop 2 of the lowest, judging by this. Woo!